going to be true, and that's something that we really need to make certain that we kind of get ingrained in our brain, that's going to be true for any rate of change function, right? So the velocity is the rate of change of position. But for any rate of change function, we can just find, if the function is always positive, we can just find the area bounded between the curve and the x-axis, and that would give us the total distance traveled, or the change in the original function if we're dealing with a different rate of change function. Okay, so let me draw a sketch here. Wrong guy. Okay, so we're looking at the interval from 3 to 21. And this function, it's kind of hard to tell, and really how I'm sketching it is not going to matter too much, but these values are decreasing a little bit. So I'm going to draw my function to look something like that. So this is my v of t. Okay, and so if I wanted to find the exact value for the total distance traveled, I would just be finding the area. I would be finding this area right here. Okay, and so if I found the area bounded between this velocity function and the t-axis on the interval from 3 to 21, that would give me the exact value for the total distance traveled. Okay, so we don't have any geometrical formulas that will enable us to find that exact value. And so we use this idea of a Riemann sum to approximate that area. Okay, just so that my picture doesn't get too overwhelmed, I'm going to erase that. Okay, so we're going to approximate that area by dividing it up into shapes that we are comfortable with. So we're going to be adding up areas of rectangles because we know how to find the area of a rectangle. All right, so we're given this interval. The first thing we need to do is determine the width of each subinterval. So we're taking this interval from 3 to 21 and we're going to divide it up into 3 subintervals. Okay, and so what we need to do is determine the width of each subinterval. So typically we would say delta x, but here we're using t instead of x. So we would say delta t is equal to b minus a divided by n. All right, where b is the right endpoint of my interval, a is the left endpoint of my interval, and then n is the number of subintervals. So here the left endpoint a is 3, the right endpoint 21 is b, and then n is the number of subintervals, which is equivalent to the number of rectangles. Okay, so we see that the width of my entire interval is 21 minus 3, so the width of my entire interval is 18. We're going to divide it into 3 equal subintervals, so 18 divided by 3 is going to give us 6. Okay, and so then we come over to my number line here, and we determine my subinterval. So we always start with the left endpoint 3, and then we're just going to add 6 to 3. So if we add 6, we would get 9. If we add 6 again, we would get 15. And if we add 6 again, we get 21, which is the right endpoint. So if we do that and we don't end up at the right endpoint, we did something wrong. Okay? And so we see that we have this first subinterval, we have this second subinterval, and we have this third subinterval. And so on each subinterval, I want to draw a rectangle. I can technically draw the height of the rectangle to be the function evaluated at any point on that subinterval. So I could technically pick anything from 3 to 9. In this class, we restrict ourselves to just the left endpoint or the right endpoint. So we have to be told which one we're going to use. So here we're going to use a right-hand Riemann sum. And so that just means on each subinterval, we're using the right endpoint. So on the first subinterval, which is from 3 to 9, what's the right endpoint of that subinterval? 9, okay? And so we're going to use the function evaluated at 9 to determine the height of the rectangle on that first subinterval. So the right endpoint is 9. So I'm going to go up to the function using that right endpoint of that first subinterval, and that's going to be the height of my first rectangle. And I do that for each subinterval. So if I'm on my second subinterval from 9 to 15, the right endpoint of that subinterval is 15. So I'm going to use the function evaluated at 15 to determine the height of the rectangle on that second subinterval. And then on that third subinterval, the right endpoint is 21. So I'm going to use the function evaluated at 21 to determine the height of the rectangle on that third subinterval. And so I want to add up the areas of these 3 rectangles, and that's going to give me a pretty good approximation to that area that I originally had drawn. Okay? And so I can use my table to determine the coordinates of those points. So we know when t is 9, the function is 364 over 9. So 9, comma, 364 over 9. 15, when t is 15, the function is 604 over 15. And when t is 21, the function is 844 over 21. Okay, and so we're trying to approximate the total distance traveled on that interval. And we know that we're going to approximate this. So when you're dealing with a Riemann sum, we're going to use an R to represent that we're using the right hand of each subinterval, and then our subscript is just the number of subintervals, so 3. So we're approximating the total distance traveled with a right Riemann sum with 3 subintervals. And that's just going to be adding up the areas of those 3 rectangles. So that first rectangle has a width of 6. It has a height, I'm going to write it as V of, I'm going to write it as V of 9 for now, and then I'll plug it in a second, just so that we know where we're getting these numbers from. Plus, the area of that second rectangle has a width of 6 and a height of V of 15. And then that third rectangle has a width of 6 and a height of V of 21. And so 6 times 364 over 9, that would give me the area of the first rectangle, plus 6 times 604 over 15, that would give me the area of the second rectangle, plus 6 times 844 over 21, that would give me the area of the third rectangle. I'm not going to take the time to type that into my calculator, but if I did, I would get 76168 over 105. And what are the units associated with that number? Okay, so this is a part that tends to cause some confusion. And so just think about the computations we did, okay? So the units along the t-axis had, the values along the t-axis had what units associated with them? So t is in what? Seconds, okay? And so we were taking a number that had seconds associated with it, and then we were multiplying by the height was a value associated with V of t. V of t was in feet per second. So we had a number dealing with seconds, and then we were multiplying by a number that involved feet per second. And so the seconds canceled out and leave us just with feet, which should make sense because we're trying to find, this approximates the total distance traveled, and the total distance traveled should be in feet. Okay, so we are trying to find the exact value for the total distance traveled. It would be the area under this curve from 3 to 21. We don't have knowledge to be able to find that using geometry. So we instead use a Riemann sum to approximate that area. And y'all are giving me very little feedback. So are we understanding? Yes. Yeah, so the question is, why is it not feet squared? And so it's a matter of the units associated with each, right? So if we were dealing with a geometric figure that had feet associated with both the length and the width, then yeah, it would be feet squared. But here, the units associated with the t-axis, t is in seconds, and then the v of t axis, it's in feet per second, right? And so the numbers, we're not dealing with just a geometric shape, we're dealing with this scale on my coordinate system, right? And so along the horizontal axis, t is representing seconds, and then along the vertical axis, the v of t is representing feet per second. So we're multiplying these numbers together, one that represents seconds, one that represents feet per second, and so they cancel out and give us feet. Yeah, good question. Other questions? Are we just exhausted, or are we okay? We're good? Okay, I'm getting nothing. All right, so let's go ahead. Any questions on Zoom? All righty, and we'll keep moving. All right, so number 2 says, given the graph of f of x below, estimate the net area between the graph of f of x and the x-axis on the interval 0 to 8 using 4 subintervals of equal width and a left-hand Riemann sum. Okay, so this little word is a word that you need to pay attention to, right? So being asked to find area and being asked to find net area are two different things, okay? So they're the same thing if the function is always positive, right? But if the function is sometimes positive, sometimes negative, they're different. And so what do I mean when I say net area? What is net area? Yes. Mm-hmm. Correct. So net area is we're looking at the regions bounded between the curve and the x-axis. If the region is above the x-axis, we count it positively. If the region is below the x-axis, we count it negatively. Okay? And so the good news is when we are computing a Riemann sum, we don't have to get caught up on which one we're adding and which one we're subtracting. It will automatically do that for us because of the coordinates being positive or negative. The y coordinates will be positive or negative, and so therefore it will automatically give us the net area. Okay, so let's take a look at this. So first thing we need to do is figure out the width of each subinterval. So we need to find our delta x. That's always going to be b minus a divided by n. All right, so a is the left endpoint of my subinterval, so a is 0. 8 is the right endpoint of my interval, sorry, so 8 is b, or b is 8. And then n is the number of subintervals, so here n is 4. All right, so the width of my entire interval is 8 minus 0, divided by the number of subintervals. So my width of my entire interval is 8. I'm dividing it into 4 equal subintervals, so I'm dividing it into subintervals with a width of 2. Okay? And so if we come over here, we're starting at 0, the left endpoint, and then we're just going to add our delta x. So if I add 2 to 0, I get 2. If I add 2 to 2, I get 4. If I add 2 to 4, I get 6. And if I add 2 to 8, if I add 2 to 6, I get 8. Right? So the 0 to 2 is my first subinterval, 2 to 4 is my second subinterval, 4 to 6 is my third subinterval, and 6 to 8 is my fourth subinterval. So again, we can use any point on the subinterval to determine the height or to draw my rectangle. But in this class, we're always going to use the left or the right endpoint, and it always has to tell us, right? So we're going to use the left endpoint. Okay, so on the subinterval from 0 to 2, the left endpoint of that subinterval is 0. So that's what we're going to use to draw the rectangle on that first subinterval. So we're going to, at 0, go up to the function, up or down, whichever way it is. And then that is going to be my rectangle for that first subinterval. Okay. On the subinterval from 2 to 4, the left endpoint is 2. So I'm going to evaluate the function at 2 to draw my rectangle. So here I go down and evaluate the function at 2, and that's going to give me my rectangle on that second subinterval. On the third subinterval, it's from 4 to 6. The left endpoint is 4. So I'm going to evaluate the function at 4 to draw that third rectangle. And then on the fourth subinterval from 6 to 8, 6 is the left endpoint. So I'm going to use the function evaluated at 6 to draw that rectangle. Okay. And so here, since we end up with 1 rectangle above and 3 rectangles below, what's going to automatically happen in my Riemann sum is we're going to add the area of the rectangle above, and then we're going to subtract the areas of the rectangles below. And so this will give us an approximation to the exact value of the net area on this interval. Okay, so our net area is going to be approximated by L sub 4. So we're using a Riemann sum. We're using a left-hand Riemann sum with 4 subintervals. And so the first rectangle, the width is 2. And then we're going to multiply by the function evaluated at 0. So 2 times f of 0 would give me that area of that first rectangle. Second rectangle has a width of 2. And then we use the function evaluated at 2 to draw that second rectangle. Plus the third rectangle again has a width of 2, and then we use the function evaluated at 4 to draw that third rectangle. And then that last subinterval again has a width of 2, and then we use the function evaluated at 6 to draw that fourth rectangle. Okay, and so if we look at these points, this point here was the point 0, 3. This point here was the point 2, -1. This point here was the point 4, -7. And then this point here was the point 6, -10. And so we have 2 times 3 plus 2 times -1, right? F of 2 is -1. Plus 2 times f of 4, which is -7, plus 2 times f of 6, which is -10. So we have 6 minus 2 minus 14 minus 20. If we do that computation, we would end up with -30. Okay, so just one thing that we have to make certain we're always clear on: if you're asked to find area is always positive. Okay, so area, if you're asked to find the area, your answer will never be negative. If you're asked to find net area, your answer could be negative or positive. Okay, and so here all we're doing is we're taking the area of that first rectangle, 6, and then we're subtracting the area of that second rectangle, we're subtracting the area of that third rectangle, and we're subtracting the area of that fourth rectangle. But again, the Riemann sum automatically does that for us, so we don't have to do anything special to make that happen, because the function evaluated at those points are negative. And so then if we're looking at our picture, does it make sense that I came out with a negative value? Yeah, so we have more area below the x-axis and above, and so that should make sense that our approximation here is negative. Okay, questions on number 2? We're feeling okay? Still good? All right. Let's look at number 3. So use a Riemann sum with 5 equal subintervals and write endpoints to approximate the definite integral from -1 to 5 of x cubed minus 3x squared plus x minus 3. Okay, so this is our first example tonight where we see a definite integral. Last week, we were talking about indefinite integrals, so we need to make certain that we understand the difference. So notation-wise, what's the difference between an indefinite integral and a definite integral? How do I know this is a definite integral compared to what we talked about last week? Bounds, right? So we have limits of integration. So when we have limits of integration, we are dealing with a definite integral, and therefore my answer should be what? So if I'm being asked to evaluate a definite integral, what should my answer be? A family of functions, like we talked about last week? No, my answer should be what? A number, right? So my answer should be a number, and what does that number represent? I heard you start to say it. Almost. So it would be the area if the function was always positive. If the function is sometimes positive, sometimes negative, it's going to represent the net area. Okay? So let's make certain we're connecting all this together. So if I don't have those limits of integration, then that is an indefinite integral, and my answer should be a family of functions. Right? That's just that. If it's an indefinite integral, it's just telling me to find the antiderivative of the integrand, and we know the answer is not unique. We know it differs by a constant, and so we end up with a family of functions. So always make certain you realize whether or not we're dealing with a definite integral or an indefinite integral. Okay, so okay, that was interesting. Okay, so we know we're dealing with a definite integral, and so we know if we could graph this curve, x cubed minus 3x squared plus x minus 3, we could graph the curve and we could find the regions bounded between the x-axis and the curve on the interval from -1 to 5. We would count the areas above the x-axis positively, the areas below negatively, and that would be our exact answer. And so instead of doing that, we're going to draw rectangles to approximate that. Okay? And so it could be beneficial to know what this curve looks like, but you don't need to know what the curve looks like to be able to set this up. So in general, I tend to always kind of come off to the side and just draw a number line with a sample curve, okay? You don't have to have it drawn correctly, and this is not going to be drawn correctly, but I'm going to call this integrand f of x, and this is just going to be a sample curve here. So because the main thing I need to do is figure out what values I need to evaluate the function at. All right, so I'm going to say f of x, and this is in no way drawn accurately. So this is not drawn accurately. Ooh, accurate. Okay, so it's just a sample curve so that I can figure out what values I'm needing to plug into the function. All right, so my interval I'm dealing with here is the interval from -1 to 5. All right, so I'm going to start over here at -1. So we know that my A is -1, my B is 5, and then I'm dealing with 5 equal subintervals, and so that is the value of my N. So the first thing we always have to figure out is our width of each subinterval. So that delta X is B minus A divided by N. So 5 minus a -1, so the width of my entire interval is 6. I'm going to divide it into 5 equal subintervals. So 6 divided by 5, if I write that as a decimal, which is probably the easiest thing to do here, is 1.2. Okay, so then we need to figure out our subinterval. So we're starting at -1 and we're adding 1.2 to get each subinterval. So -1 plus 1.2 gives me 0.2. 0.2 plus 1.2 gives me 1.4. 1.4 plus 1.2 gives me 2.6. 2.6 plus 1.2 gives me 3.8. 3.8 plus 1.2 gives me 5. All right, so if we do it correctly, we should always end up exactly at B. And then again, this is my first subinterval, my second subinterval, my third subinterval, my fourth subinterval, and my fifth subinterval. Okay? So then we have to determine whether or not we're using the left or the right endpoint on each subinterval. So we're told we're using the right endpoint on each subinterval, and so then now we just need to draw our rectangles. So for our first subinterval from -1 to 0.2, the right endpoint is 0.2, and so we're going to use 0.2 to draw that first rectangle. Okay. On my second subinterval, it goes from 0.2 to 1.4. Excuse me, the right endpoint is 1.4, and so we're going to use the function evaluated at 1.4 to determine the height of my rectangle. The third subinterval is from 1.4 to 2.6. 2.6 is the right endpoint, so we're going to use the function evaluated at 2.6 to determine the height of my third rectangle. Fourth subinterval, we're going to use the function evaluated at 3.8. And then fifth subinterval, we're going to use the function evaluated at 5 to draw my rectangle. Okay, so the integral from -1 to 5 of x cubed minus 3x squared plus x minus 3 dx, we are approximating this with an R sub 5, right? That's a Riemann sum with 5 subintervals, and we're using the right endpoints. And we're just adding up the areas of these 5 rectangles. Okay, so the width of the first rectangle is 1.2 times the height is the function evaluated at 0.2. Plus the second rectangle, the width is 1.2 times the height is the function evaluated at 1.4. Plus the third rectangle, they all have a width of 1.2 times the height is the function evaluated at 2.6. Plus the fourth rectangle, come down here, the width is 1.2 times the height is the function evaluated at 3.8. Plus the fifth rectangle, the width is 1.2 times the height is the function evaluated at 5. Okay, so I'm going to go ahead and put this function into y1 on my calculator. But I can find these values. So y1 is x cubed minus 3x squared plus x minus 3. And so then I can evaluate this either on the home screen or on my table. If I want to use my table, I need to hit second window, go to my table set and change the independent to ask. So if it's on auto, I need to arrow over to ask and hit enter. And then if I hit second graph, that will take me over to my window, I'm sorry, to my table. And so I'm wanting to evaluate this at 0.2, 1.4, 2.6, 3.8, and 5. If you're using the table, you're not going to be able to see the whole thing, so you have to scroll over, and then down at the bottom it will show you the unrounded value. So negative 2.912, negative 4.736, negative 3.104. So I guess here they actually are all displaying in there, but sometimes they're not. 12.352 and 52. Right. So if we come over here, that's 1.2 times negative 2.912 plus, let's scoot down a little bit so we don't run into that. All right, so 1.2 times negative 2.912 plus 1.2 times negative 4.736 plus 1.2 times negative 3.104 plus 1.2 times 12.352 plus 1.2 times 52. And if I did that computation, we would end up with 64.32. Okay, so based on my computation now, I can tell that my graph is definitely not correct, right? Because but it doesn't matter, right? So we just need to be able to know what values of x we're evaluating the function at to draw our rectangles. It doesn't have to be drawn accurately, but now with doing our computation, we know how many of our rectangles would be above the x-axis. 2, right? So just the last 2 had the function evaluated those values of x was positive. So those last 2 rectangles would actually be above the x-axis. The first 3, the function evaluated at those values was negative, and so those rectangles would be drawn below the x-axis. But it turns out that there's a lot more area above the x-axis, right? Because we ended up with a positive value. So even though if it was drawn accurately, we'd have 3 rectangles below and 2 above, the areas of those 2 above would be a lot larger than the areas of the rectangles below, because it came out to be a positive value. Yeah. Okay, so you put the function into y1, and then you hit second window. So above window it says table set, and so what you're having to do is set up the table, and you just need to change the independent to ask. So just arrow down to independent, select ask, hit enter. And then once you have that set up, then you can just go over to the table, and to get to the table, you hit second graph. And then you can just type the values in. Yeah, you're welcome. Sometimes I will mention the table is nice when the values come out to be nice, okay? But if the value, like here, the values came out to be nice. If they didn't come out to be nice and you're needing exact answer, it would be in your best interest to do it on the home screen. So you'd hit bars, y bars, function, y1, and then you would evaluate it at, for instance, 0.2. Because that way, if you needed to convert it to a fraction, you would have to do that on the home screen. You couldn't do that in the table. So make certain you're comfortable with both of those. Okay, so questions on number 3. Okay, so let's keep going with this idea of the definite integral. All right, so use the figure below to evaluate the following integral. All right, so this is a definite integral from 3 to 6, where my integrand is x squared plus 2f of x. And we're integrating with respect to x. And we're given a graph of f. Okay, so if my integrand was just f, then I could use this graph and use the idea that the definite integral represents the net area, okay? But my integrand here is not just f. So we would need to here use properties of the definite integral to get it to the point where part of what I'm trying to find is just the definite integral of f of x, okay? Can anyone see kind of a first step of what we could do to get there? So right now my integrand is this whole thing, and I can only use this graph if my integrand is just f of x. We're lively this evening. I'm making this really fun. Okay, so we learned some properties of integration. And we actually used this last week with indefinite integrals, right? So if we were trying to find the indefinite integral or find the antiderivative of a sum, what were we able to do? Okay, so if we were dealing with a constant, right? So if we were trying to find the antiderivative of a constant times a function, we discussed last week that that's just the constant times the antiderivative of the function. We are going to need to use that in a minute. But before we can use that, we can use the fact that we have this sum, right? And we know that the integral of a sum is the sum of the integrals. Okay, so that idea held for derivatives. That idea held for indefinite integrals, and it holds for definite integrals as well. Okay, so we need to make certain we realize that this is the same as the integral from 3 to 6 of x squared dx plus the integral from 3 to 6 of 2 f of x dx. Right? And so now my integrand is almost just f of x, but the only issue is that 2. But like she just said, we know the integral of a constant times the function is just the constant times the integral of the function. And so we can pull that 2 out in front. Just so I don't have to rewrite it all, I'm just going to erase it and put it out in front. Okay, so we now have 2 integrals that we need to find the value of. One involves f of x and one doesn't. So we have this integral here, which I'm going to call A, I guess. And then we have this integral here, which I'm going to call B. All right, so let's start by working on A. All right, so we're trying to find the integral from 3 to 6 of x squared dx. Okay, and so we recall that if we're trying to find the integral from a to b of little f of x dx, how do we do this? Okay, so yeah, so if we are trying to evaluate this definite integral, if I'm just looking at it in general, what do I need to find here? Yes, Isaac. Yes, okay, so we need to find the antiderivative, right? So you learned what was known as the fundamental theorem of calculus, part 2, I believe. And I don't, did y'all call it part 2 or part 1? I'm trying to remember. It's been a little while. But part 2, I believe. And we find the antiderivative, right? So little f, to represent the antiderivative of little f, we use capital F of x. and then we evaluate it from A to B. So capital F of B minus capital F of A. Okay? And so here in part A, we are trying to find the value for the definite integral from 3 to 6 of x squared dx. So we need to find an antiderivative of x squared. What type of function is x squared? So this is an exponential function. It's a power function, so we can use that backwards power rule. We add 1 to the power, so 2 plus 1 gives us 3. We divide by that new power out in front. All right, so one antiderivative of x squared is 1/3 x cubed. All right, so we can use any antiderivative. So just to make our lives easier, we choose the c to be 0. But you could technically add any number here, and since you're subtracting these two expressions, it would cancel out, so it doesn't matter what value of c you choose, but I'm going to use just 1/3 x cubed, and then I'm going to evaluate this from 3 to 6. So I'm going to plug in the upper bound, so 1/3 times 6 cubed, minus, I'll plug in the lower bound, 1/3 times 3 cubed. And I'm not going to take the time to type that in, but that's going to give me 63. We know that x squared is always positive, right? If we were to look at the graph of x squared, that tells me that the area bounded between x squared and the x-axis on the interval from 3 to 6 is 63. Okay? All right, so that is that first part. Now we need to find b. So b is the integral from 3 to 6 of f of x dx. Right? So now we see that this is matching what we are looking at here in our graph. And so this curve is f of x. If I'm wanting to find the definite integral from 3 to 6, that just means I'm finding what? So if I'm looking at this graph and trying to find the definite integral from 3 to 6, graphically I'm trying to find the net area. All right, so the definite integral represents the net area. And so here we're looking at the interval from 3 to 6. So we see that on the interval from 3 to 5, it's above the x-axis. On the interval from 5 to 6, it's below the x-axis. And so we are just going to find the net area by finding the area above and then subtracting the area below. Since the regions divide into geometric shapes that we know how to find the area of, this is going to be the exact value for this definite integral. Right? So it's only when the graph is curved, right, where it's not a shape that we are familiar with, that we have to use Riemann sums to approximate it. Okay, so here we see we have this rectangle. Right, we have this rectangle and this triangle above, and then we have that triangle below. So the area of this first rectangle, that width is 1 and its height is 4. The area of this triangle would be 1/2 times the base is 1 times the height is 4. And then minus the area of this triangle below, which would be 1/2 times the base is 1 times the height is 4. So if we do that computation, we would get 4. Okay, so then plugging in above, we know that A is 63, so we have 63 plus 2 times B is 4. So we get 63 plus 8, which gives us 71. Okay, so that's a nice problem where it is combining a lot of ideas into one problem, right? So it's testing us on our properties of the definite integral to be able to break that up. It's testing our knowledge of the fundamental theorem of calculus, and it's testing our idea that the definite integral represents the net area. Yes. On B? No. Yeah, so on B, so if you remember, the idea of the definite integral was introduced as the net area in section 4.3. And then in 4.4, we went on to say, okay, one way we can find it, if we can't find the exact value with using the ideas of net area, is using the fundamental theorem of calculus, right? So there's two different ways of finding the value for the definite integral. If it's a simple graph like it is here, you can find it just by using the idea of net area. Majority of the time, the graph is more complicated than this, and so if we're wanting to find the exact value, we would have to use the fundamental theorem of calculus. Mm-hmm. I mean, the fundamental theorem of calculus holds for both of them, but we don't know the antiderivative, and it would be more work if we wanted to try to find it, right? So yeah, so the fundamental theorem of calculus would hold in part B, but we don't have that information here, but we have the graph, and so we can find the net area just by looking at the graph. Yeah, you have two choices. Yeah. Because this 2 was right here from the beginning, right? So here when we started, our integrand had a 2 there, and so we to get what we had written on the right hand side there, we were using our properties of the definite integral. And so the integral of the sum is the sum of the integrals, and then the integral of a constant times a function is just the constant times the integral of the function. Good questions. Welcome. Any questions on Zoom? Are y'all still there? Yes. Yes. So yeah, so you did learn in 4.4 that fn int command will give you a decimal approximation. Sometimes it'll come out to be the same, sometimes it'll come out to be close. But yeah, here you could do that. But realize because of that, to make certain that you know how to do it by hand, oftentimes we'll put a variable in one of the limits of integration to make certain that you know how to use the fundamental theorem of calculus. Yeah, and we'll probably see that here in a minute. Maybe even the next one, we'll see. Yep, the next one. Okay, any other questions before we, question? Correct. Yeah. Yeah, so it's always plugging in the upper limit of integration and then plugging in the lower limit of integration and subtracting. Okay. All right, so let's go ahead and look at number 5. So evaluate the following integral. So it's kind of like what I was just saying, that to force you to do it by hand, oftentimes we'll put one of the limits of integration to be this unknown value, okay? So evaluate the following integral, the integral from k to 4 of 15x to the 4th minus 6 over x to the 5th minus 2x plus 8 dx. Okay, and so we're needing to use the fundamental theorem of calculus, right, because we're not given a graph. So we're needing to use the fundamental theorem of calculus to evaluate this. But to be able to use the fundamental theorem of calculus, we need to be able to find the antiderivative of my integrand. All right, and so we went through this thought process last week, that if my integrand is written as a sum or difference of basic functions, I can just use my antiderivative rules and find the antiderivative of each piece and leave my sum or difference in between. This integrand is not written as a sum or difference of basic functions. can I rewrite it as a sum or difference of basic functions? If I had a quotient, what would have to be true for me to be able to rewrite it? This is something we discussed last week. Right, we need to have like a single term in the denominator, right? If we had just a single term in the denominator, then we could break it up into separate fractions, do simplification, and then use our ideas from 4.1 to find the antiderivative, okay? But as we discussed last week, if we can't use the ideas of 4.1 to find the antiderivative, what's our only other choice to find the antiderivative? U substitution, okay? And so we know that when we are using U substitution, we are, oh, hold on. Question on Zoom?
Yes. So in some questions on like problems or quizzes, it always says that note that k is less than 4.
Mm-hmm.
Does this also happen in this question?
Yeah, so technically it won't change anything here, but yes, that would be if you wanted to be able to interpret it in terms of net area, your lower limit of integration would need to be less than your upper limit of integration. But technically, here k could be any real number.
Okay, thank you.
You're welcome. And just real quick, if you drew on the screen on Zoom, if you don't mind erasing it, I'd appreciate it. Thank you. Thank you. Okay, so let's go ahead and take a look at this. So if we're dealing with U substitution, we know that we're in one of 3 cases, right? So we discussed this last week and this is going to be kind of informally put, but the integral of a function raised to a power times some other stuff. We're dealing with 1 over a function times some other stuff, or we're dealing with b raised to a function times some other stuff. Okay, so remember, U substitution is just enabling us to simplify something that was the result of the chain rule, or nearly the result of the chain rule. And so to determine what my U is, I just need to identify which of these cases I'm in. So wherever I see the word function, that's what we would identify as our U. Okay, so the question is, which of these 3 cases am I in? Am I in case 1, 2, or 3? 2. All right, so hopefully we can see, and sometimes by process of elimination we can figure out which one we're in. But I definitely don't have a constant raised to a function anywhere, so it's not case 3. Case 1, we don't have a function written to a power. As I mentioned last week, if we have the entire denominator raised to a power other than 1, we would want to bring it up to the top, and then we would be in that case that we have a function raised to a power. But when the entire denominator is not raised to a power, we want to leave it there. Okay, so I'm going to take this and rewrite it so that I can see that case 2. So the integral from k to 4 of 1 over a function, so 1 over x to the 5th minus 2x plus 8 times 15x to the 4th minus 6 dx. All right, so I just split that up so that I can see that we are dealing with 1 over a function times some other stuff. Okay, so then that function in the denominator is what we're going to identify to be our U. And so then we come off to the side and we define U to be x to the 5th minus 2x plus 8. And then we follow the same process that we did back when we were dealing with an indefinite integral. we state that du is equal to, and then we take the derivative of our u with respect to x. So the derivative of this would be 5x to the fourth minus 2. And then we put that in parentheses, dx. At this point, people have a variety of preferences, but my preference would be then to see if there's a constant that they have in common, pull that constant out in front, and then divide both sides by that constant. But here we see 5 and 2 don't have anything in common that we can factor out in front. Okay, we look back at our integrand, and at this point we're hopeful that my du would take care of everything else in the integral. We see that it doesn't exactly match up, and so our other option is to come over here and see if there's something we can factor out of both of these, and we see that yes, we can factor out 3. So we have the integral from k to 4 of 1 over x to the 5th minus 2x plus 8. I'm just going to factor out a 3. If I factor out a 3, I'm left with 5x to the 4th minus 2 dx. And so now things match up, right? So this x to the 5th minus 2x plus 8, that's exactly how our u was defined. So we're going to replace that with a u. And then our 5x to the 4th minus 2 dx, that is exactly equivalent to du. And so it's okay for constants to remain in our integrand, but we need to get rid of everything that involves an x. And so here in my integrand, I have achieved that goal. Okay, and so we keep in mind that here we are not dealing with an indefinite integral like we were last week. And so we have to be careful because the limits of integration on my integral are limits of x, okay? And so while I've transformed everything in my integrand to be in terms of u, my limits of integration are still in terms of x, okay? And so I keep in mind that this is x is equal to k and x is equal to 4. We need to transform everything to be in terms of u. So when doing u substitution, on a definite integral, we must change our limits of integration to be in terms of u. Okay? So my lower limit of integration initially was x equals k. So when x equals k, the question is, what is u? Well, u is defined to be x to the 5th minus 2x plus 8. So I'm plugging in k for x. So u is k to the 5th minus 2k plus 8. So when x equals k, u is k to the 5th minus 2k plus 8. My upper limit of integration was x equals 4. When x is equal to 4, u is equal to 4 to the 5th minus 2 times 4 plus 8. Which I believe gives me 1,024. Okay, so when I write my new integral in terms of u, I have 1 over u times 3 du. My lower limit of integration now needs to be a limit of u, which is k to the 5th minus 2k plus 8. My upper limit of integration is u equals 1,024. Okay, so dealing with u substitution on a definite integral differs from dealing with u substitution on an indefinite integral in two ways. One way is that we have to change our limits of integration as well. The second way it differs is since a definite integral is a number, for this problem it's going to be an expression involving an unknown number k, but in general it's a number. We don't have to go back to the x's, okay? And so now we can just continue on as if we had a definite integral that didn't involve u substitution. So I can pull that constant out in front. So we have 3 times the integral of k to the 5th minus 2k plus 8. The upper limit of integration is 1024, and then my integrand is 1 over u. And so then now we just use the fundamental theorem of calculus, which tells us that we just need to find the antiderivative of 1 over u. The antiderivative of 1 over u is the natural log of the absolute value of u. And then now I need to evaluate this at the lower and upper limits of integration. So if I plug in the upper limit of integration, I get 3 natural log of the absolute value of 1024, minus if I plug in the lower limit of integration, I get 3 natural log of the absolute value of k to the 5th minus 2k plus 8. Okay, and so there's a lot going on in that problem, but just keep in mind that when you're dealing with u substitution on an indefinite integral, your last step is to then give your answer in terms of x instead of in terms of u. But when you're dealing with a definite integral, your answer is a number, and so you use the fundamental theorem of calculus and you just get your answer. You don't have to go back to what the x's were representing. All right, questions on that? Yes? Like on this line right here, why didn't I write du over dx and then move it to the right-hand side? Yeah, so there are a wide variety of minor tweaks in terms of how people do u substitution. So if you do it slightly different, it's most likely completely fine, right? So there's, over the years, I've seen, people who like to always solve for dx, or they like to, there's lots of different ways to go about it. But this is the way that it was introduced in the notes. But what you're saying right there sounds like it would be okay. Yeah. You're welcome. Yes. Yeah, so the main thing is that, so the question was re-explaining the limits of integration. So the main thing is that this dx on this original problem is telling us that we're integrating with respect to x. And so these numbers right here are values for x, all right? And so this original integral is saying that x is going from k to 4. So when we are transforming our integral using u substitution, not only do we need everything in the integrand to be in terms of u, we need those limits to be in terms of u as well. And so we just look at the definition of u to figure out what u is when x is k and x is 4. And we just plug in to our definition of u to get the new limits of integration in terms of u. All right, so let's look at number 6. So use the graph of f prime of x below and the fact that f of 1.5 is equal to 9 to find f of 6. All right, so there's a handful of problems in this chapter that it's kind of really hard to see where to start. And this is one of those problems where you're looking at this and knowing what to do with it is kind of challenging. Okay, so let me try to convince you of how I know this is what we should do to solve this problem. All right, so we notice that the graph is of the derivative. All right, so that's the first thing. So we notice the graph is of the derivative, and I'm noticing that the derivative is just dealing with some straight lines, and I can find areas dealing with this graph pretty easily. All right, and so if I'm thinking about maybe needing to find area, I keep in mind that the definite integral of a function represents the net area. And so again, this is kind of my thought process to help me decide this is what I need to do. Okay, and so I recall that if I am integrating from a to b a rate of change function f prime of x dx, right? So if you look back at where I wrote the fundamental theorem of calculus before, the integrand was little f of x. And there's not an easy way to represent the antiderivative of little f of x. And so we use capital F of x to represent an antiderivative. But when my integrand is f prime of x, I have a nice way to represent the antiderivative of f prime of x, right? Because if I had little f of x and I took its derivative, I would get little f prime of x. Now I'm wanting to find the antiderivative, so I'm just going one step back, and so that gives me little f of x. Okay, and so we know the antiderivative of little f prime of x is little f of x, and then we could evaluate it from a to b, and so that would give me little f of b minus little f of a. Okay, so I see that I have a graph of f prime of x. I know the definite integral of f prime of x would be dealing with the areas, and then I know the fundamental theorem of calculus tells me that that's the same thing as the original function, the change in the original function, so f of b minus f of a. And I see that that's the other information I'm given here. I'm given f of 1.5 is equal to 9, and then I'm wanting to find f of 6. Okay, so all of that together is convincing me, hopefully, and convincing you as well, that I can use the idea that the integral, right, so my two different values of x are 1.5 and 6, right? So this is going to be my a, this 1.5 is going to be my a, and this 6 is going to be my b. So the integral from 1.5 to 6 of f prime of x dx is little f of 6 minus little f of 1.5. Right, so again, it's hard, it's one of those problems that's hard to convince you that this is where we need to head, but hopefully with that explanation, you can kind of see what led me to this conclusion. Yes, Madison?
So if the 1.5 and the 6 were switched, would it still be the same where the 6 is at the top and the 1.5 is at the bottom, or would those also switch?
Yeah, so good question. So if the 1.5 and the 6 were switched, it wouldn't matter in terms of if I was using my fundamental theorem of calculus. You would just take whichever numbers on the top and whichever numbers on the bottom, and you would subtract them in that order. But we do have to be careful when we're looking at a graph and interpreting it in terms of net area. So if we switch them, then yes, we'd have to switch them over here as well, but then we couldn't interpret this as the net area. So when we are looking at a graph and using this idea of net area, my lower limit has to always be smaller than my upper limit. And if it's not, then I would need to use my properties of the properties of the definite integral and switch it and put a negative sign out in front.
Okay, thank you.
You're welcome. Okay, so we need to find these pieces, all right? So we're wanting to find f of 6, right? That's what we're trying to solve for. F of 1.5, we're told, is 9. And so all we need to find is this piece right here, the integral from 1.5 to 6 of f prime of x dx. We see f prime of x is always positive. So all I'm needing to find is the area bounded between this curve and the x-axis on the interval from 1.5 to 6. Okay, so I just need to find this area. All right, so I'm going to divide it up into some shapes. You could divide it up, possibly differently than me. But I see I have this square, and I have this rectangle, and I have this triangle. So I'm just going to add up the area of that square, that rectangle, and that triangle. So that square, keeping in mind that each tick mark is a half a unit, the square has a width of 1.5 and a height of 1.5. So this is 1.5 times 1.5. The triangle, the area of that triangle is 1/2 times the base, which is 1.5, times the height, which is 0.5, because each tick mark is representing a half a unit. And then plus the area of this rectangle, it goes from 3 to 6, so the width is 3, and then the height is 2. So that area I believe is 8.625. So then that goes up here. And so we know that 8.625 is equal to f of 6 minus 9. We add 9 to both sides, we get f of 6 is equal to 17.625. Okay. So this, again, a lot of these problems can really connect a lot of ideas all into one problem. So this is connecting the idea of the fundamental theorem of calculus with the idea that the definite integral represents the net area. And so it's kind of a puzzle trying to use what we know to find the missing piece. Okay, so one more problem before we kind of go back to the beginning of the material on the exam. So the marginal revenue function for a product is given to be r prime of x is equal to 20 minus 0.2x dollars per item when x items are sold. Find the change in revenue when the number of items sold changes from 20 to 45. Okay, and so this is very much in line with what we saw above, that when we integrate a rate of change function, we get the net change in the original function, right? So when you see this, what I just said in words, hopefully is what you see. So what I said in words is that if we integrate a rate of change function, right? So the derivative is a rate of change function. It's going to give us the net change in the original function, all right? So here, we're given a rate of change function, the marginal revenue function, that's the derivative of the revenue. And that is going to give us the net change in the original function. And so that's what we are trying to find here. So the change in revenue from x equals 20 to x equals 45 is the integral from 20 to 45 of the rate of change function, r prime of x. If we plug in what r prime of x is, we have 20 minus 0.2x dx. And so we could do this by hand by finding the antiderivative of 20 minus 0.2x and then plugging in the upper limit, excuse me, and the lower limit and subtracting. Or we could just use the fnint command on your calculator. So since I haven't shown you that, I'm just going to use the fnint commands, but we'd have 20 minus 0.2x, comma x, comma 20, comma 45. Most of your calculators, my calculator won't do it symbolically, but for most of your calculators, you'll have the integral symbol and you'll have all these boxes to fill in. And so if you have just the boxes, the lower box you put 20, the upper box you put 45, the integrand you do 20 minus 0.2x, and that last box you do x. My calculator on the computer is an older version and it won't do that, but if I do math fnint, I have to do it 20 minus 0.2x, comma x, comma 20, comma 45. But I just wanted to show you that use of that fnint command. This gives us $337.50. But again, that wasn't a hard integral to do by hand. You could totally, very easily do that integral by hand. All right, so that concludes the part over the new material. So that was all over 4.3 and 4.4. So now we're going to go back and talk about the beginning sections that were on, that are going to be on this exam. All right, so the number 8 says find the absolute extrema of f of x is equal to x squared minus 21 all over x plus 5 on the interval from -4 to 1. Okay, so anytime we are talking about absolute extrema, the first thing we need to do so that we don't reach any incorrect conclusions is to observe the domain. So what values of x are not in the domain of this function? -5. So I'm not going to write it in interval notation, but I'm just going to say x can't be equal to -5 because I just want to keep that on my mind. Okay, so we know that in this class our functions are continuous on their domain. Is this function continuous on this interval from -4 to 1? Yeah. All right, so -5 is not on that interval. So therefore, we are dealing with a function that is continuous. And since my interval has square brackets on both sides, we are dealing with a closed interval. All right, so we are dealing with a function. We have all right, can y'all hear me on Zoom? My microphone died.
Yes, we can hear you.
Okay, thank you. So we have a function that is continuous on a closed interval. So therefore, we can use the closed interval method. All right, so the extreme value theorem tells us that if we are dealing with a continuous function on a closed interval, we are guaranteed to have both an absolute max and an absolute min. And the closed interval method tells us that we are guaranteed that the absolute extrema will occur either at an endpoint or what? A critical value. Okay, so all we need to do is find our critical values on this interval and then evaluate the function at the endpoints and at the critical values on this interval. So to find the critical values, we need to find the derivative. Kind of hard to switch our brain now, but now going back to derivatives, if we want to find the derivative of this, what do I need to use? A quotient rule. So we have the denominator x plus 5 times the derivative of the numerator. The derivative of the numerator is 2x minus the numerator, x squared minus 21, times the derivative of the denominator. The derivative of the denominator is 1, all over the denominator squared, x plus 5 quantity squared. So if we do a little bit of simplifying here, if we distribute this 2x, we get 2x squared plus 10x. If I distribute this negative sign, we have minus x squared plus 21 all over x plus 5 quantity squared. 2x squared minus x squared gives us x squared plus 10x plus 21 all over x plus 5 quantity squared. I'm going to go ahead and try to factor that numerator. So if I try to factor that, that's going to factor into x plus 7 times x plus 3, right? Because x squared plus 3x plus 7x gives us that plus 10, and then plus 21. All right, so we know that f prime of x is 0 when the numerator is 0. So x plus 7 times x plus 3 is equal to 0. So when x plus 7 is equal to 0, or x plus 3 is equal to 0. So x is equal to negative 7, or x is equal to negative 3. The derivative does not exist when the denominator is equal to 0. So when x plus 5 is equal to 0, x is equal to negative 5. So we see that negative 7 is not on our interval. Negative 5 is not on our interval. So negative 3 is the only critical value on our interval. Okay, so we make a table, and we're going to plug in the left endpoint of negative 4, the critical value of negative 3, and the right endpoint of 1. I want to plug in these values of x into what? The original function. Okay, so we could take that original function and put it into y1 on our calculator. Y1 is x squared minus 21 divided by x plus 5. I go to my table, figure out my values, plug in negative 4, negative 3, and 1. I get negative 5. Negative 6 and negative 10/3, which is approximately negative 3.33. And so then the easy part is just looking at those three values, determining which one's the largest and which one's the smallest. And so we would say that we have an absolute max of negative 10/3 at x equals 1. And we would say we have an absolute min of negative 6 at x equals negative 3. Okay, so that example is our practice from section 3.4, but again, you can look back at a previous week in review to get more practice for 3.4. Let's go ahead and look at the next example for some practice from 3.5. So a box with a square base and an open top is being constructed to have a volume of 80 cubic meters. The material for the base costs $5 per square meters, and the material for the sides costs $2 per square meter. Find the dimensions of the box that will minimize the cost of materials. Okay, so let's take a look at this. So we're wanting to deal with a box with a square base. Let's do our best to draw a box with a square base. So let's see if we can draw this box with this square base. Okay, so we are trying to determine the dimensions of this box. So how many unknowns do I have? How many different unknowns do I have? Let's see. So really you might be tempted to introduce 3 variables, or you might be tempted to introduce 2 variables. And so we want to introduce as little variables as possible. And so do I need 3 variables, or can I introduce just 2? And it's a key word here, the fact that the base is square, right? You might be tempted to say like X, Y, and Z for like the base, the width, and the height. But the fact that it's square means that these 2 dimensions are the same. So I'm going to call both of these X, and then I'm going to call the height Y. Okay? So then for these optimization problems, we typically have something that is known that can be written in the form of an equation. And then we have an objective. We have something that we're trying to maximize or minimize. Okay? What is known about this box? The volume. We know that we have a volume of 80 cubic meters. And so to write that in terms of our variables, we know the volume of this box would just be X times Y, right? And so X times X is just X squared. So we know X squared times Y is 80. All right, so that's the known information. So we know that X and Y have that relationship. And then our objective is what we're trying to maximize or minimize. We're being told that we want to minimize the cost. Okay, so we want to minimize our costs. Okay, so we need to write our cost in terms of X and Y. All right, so a box with a square base and an open top, so we need to pay attention to that. So we don't need any material for the top. The material for the base costs $5 per square meter. So we know that the area of the base is just X times X. So the area of the base is X squared. And it's going to cost us $5 per square meter. So that base is going to cost us 5 times X squared. All right. Plus the material for the side, so that was the cost for the bottom. The cost for the sides is $2 per square meter. What's the area of one side? XY, right? So we know the area of each side is XY. So we have XY plus XY plus XY plus XY. So we know the total area of the sides is 4XY square meters. We know that it costs $2 per square meter. So we need to multiply that by 2. So we have 5x squared plus 8xy. Okay, so that is my cost in terms of X and Y. To be able to use the ideas from the previous section, we need to have our function be a function of one variable. And so we use the known information to be able to substitute in to get a function of one variable. And so if I solve this for y, I have y is equal to 80 divided by x squared. And then we can plug that in for y. And so we get c of x is equal to 5x squared plus 8x times 80 over x squared. We're wanting to minimize this function on some interval. Okay? So to find our interval, we need to think about what values of x and y make sense. And so we see that we're dealing with this box. And so for me to have a box, what must be true about x and y? They need to be positive. So we need x to be greater than 0. We need y to be greater than 0. All right? Since y is defined to be 80 over x squared, if x is positive, we're taking a positive number and dividing a positive number, it's always going to be positive. All right? So y will always be positive when x is greater than 0. And so what that means is to have a box, all I need is x to be greater than 0. And so my interval is just the interval from 0 to positive infinity. And so that's what I put over here, 0 to positive infinity. Okay, so for every single optimization problem, this is my goal, getting to the point where I have maximized or minimized a function of one variable on an interval. Okay, and then once I get it to that point, then I just need to use the ideas that we discussed in 3.4 to solve. Okay. So if I'm looking at this cost function, I'm going to simplify it a little bit. So 5x squared plus 8 times 80 gives me 640. X divided by x squared, I'm going to write as x to the negative 1. We see that this function, the only value of x that it's not defined at is x equals 0, right? Because that's the same thing as 640 divided by x. But that's not on our interval, so we're dealing with a continuous function on an open interval. So we can't use the closed interval method, but we can use either the first derivative test or the second derivative test. All of our methods involve needing to find the critical values, so let's go ahead and find the critical value. So find the derivative. We have 10x minus 640x to the negative 2. This is 10x minus 640 over x squared. In my opinion, the easiest thing to do in a situation like this is to get a common denominator. So our common denominator would be x squared. So we need to multiply 10x by x squared over x squared, which would give me 10x cubed over x squared minus 640 over x squared. Gives me 10x cubed minus 640 over x squared. So we know that c prime of x is equal to 0 when its numerator is 0. So 10x cubed minus 640 is 0. So 10x cubed is equal to 640. Divide through by 10, x cubed is equal to 64. Take the cube root of both sides, we get x is equal to 4. C prime of x does not exist when the denominator is 0, so x squared is equal to 0, or x is equal to 0, but that is not on our interval. Okay, so x equals 4 is the only critical value on our interval. Again, it's not a closed interval, so we can't use the closed interval method. We can use the first derivative test or the second derivative test. Okay, so since we have one critical value on our interval, it is not closed, we can use the first derivative test or the second derivative test. And you can always use either, right? So it's just a matter of preference. I tend to always use the second derivative test, but if you want to use the first derivative test, you can. So use the first derivative test or the second derivative test. I will use the second derivative test. Okay, so it's very similar to what we saw back when we talked about the second derivative test for local extrema. I need to find the second derivative. I'm going to look at the unsimplified first derivative because that's going to be the easiest one to find the derivative of. So if I find the derivative of the unsimplified first derivative, I have 10 plus 1280x to the negative 3. I'm going to plug in my critical value of 4. So I have 10 plus 1280 over 4 cubed. I don't care about that value. All I care about is the sign. It's positive. So I'm dealing with a point where I have a horizontal tangent line and the graph is concave up. And so I can conclude, since it's the only critical value on that interval, I can conclude that it is an absolute min. So we have an absolute min at x equals 4. If we look back, we were trying to minimize the function. And so we have found that our solution occurs at x equals 4. And then the last step is we need to make certain that we actually answer the question. The question was, find the dimensions of the box that will minimize the cost of materials. All right, so x is equal to, what is our units? 4 meters. Y is equal to 80 divided by x squared. So 80 divided by 4 squared. So 80 divided by 16, which gives us 5 meters. So the dimensions so remember the base was x by x. So 4 meters by 4 meters by 5 meters will yield a minimum cost. It didn't ask us to find the minimum cost, so I'm not going to find it just to save time. But if we wanted to find the minimum cost, we would just plug in that value of x into the original cost function. Yes? Why didn't I put the x cubed where? Like down here? Oh, so how did this 10x become this 10x cubed? Yeah, so I was getting a common denominator, right? So 10x minus 640 over x squared, right? So this was like over 1. And so my common denominator was x squared. So I multiplied both the numerator and the denominator over here by x squared to get that common denominator. Mm-hmm. Yes? How did I get the power to be negative here, right here? Okay. So yeah, so here we saw that, y'all have a good evening. So the function was 5x squared plus, and then right here I kind of did a little shorthand. So 8 times 80 was 640, so we had 640x divided by x squared, all right? And so the x in the numerator canceled out with one of the x's in the denominator. And so that was 5x squared plus 640 divided by x, which is the same thing as 640 times x to the negative 1. And yeah, so I just moved it up. I kind of skipped a couple of steps there, but I moved it up because if I wanted to try to find the derivative of it written like this, I would have to use the quotient rule, and I don't want to use the quotient rule if I don't have to. All right, let's go ahead and look at this next one. So if f prime of x is equal to 3x squared minus 2e to the x minus 1 over x to the 5th minus 3 over x minus 2 to the x, and f of 1 is equal to 5/4, find f of x. All right, so hopefully you recognize that what we're needing to do here, right? We're given f prime of x, and we're wanting to go backwards. We're wanting to find the antiderivative and find the original function. And so we know that when we go backwards, we find the general antiderivative, where we can add or subtract any constant c. And then we're given information to find the specific antiderivative. All right, so here, our first step is to find the general antiderivative. Okay, and so we are wanting to find the antiderivative of f prime of x. Right? F prime of x is 3x squared minus 2e to the x. Just to save some time, I'm going to do a little bit of rewriting as I copy it down. So 1 over x to the 5th, kind of like what we were just talking about, is the same thing as x to the negative 5. So I'm going to write that as minus x to the negative 5. 3 over x, if you remember, we discussed that that's the one case that we don't want to bring up to the top when we're applying our antiderivative rules, because if we did, it would give me a power of negative 1, and that's the one value of n that doesn't work for that backwards power rule. All right, so I'm going to write this as just minus 3 times 1 over x, and then minus 2 to the x dx. Okay. So we see that we're dealing with a sum and difference of a bunch of basic functions. We know that the antiderivative of a sum or a difference is just the sum or difference of the antiderivatives. So we can just apply our antiderivative rules to each piece. So for that 3x squared, if we want to find the antiderivative of 3x squared, that 3 stays there. And then we multiply by the antiderivative of x squared. That's a power function, so we have to use that backwards power rule. We add 1 to the powers, so 2 plus 1 gives us 3, and then we divide by that new power out in front. So 3 times 1/3 x cubed, minus the antiderivative of 2e to the x, that 2 stays there, and then we multiply by the antiderivative of e to the x. The antiderivative of e to the x is e to the x, minus the antiderivative of x to the negative 5. That's a power function. We use that backwards power rule, but we have to be careful since it's a negative power. So we're going to add 1 to the power, so negative 5 plus 1 is going to give us negative 4, and then we're going to divide by that new power out in front. So 1 divided by negative 4 out in front, minus a constant times a function. Again, that constant 3 is going to stay there. And then we're going to multiply by the antiderivative of 1 over x. The antiderivative of 1 over x is the natural log of the absolute value of x, minus the antiderivative of 2 to the x. Tempting to use that backwards power rule, but that's not a power function. That's an exponential function. And so the antiderivative would be 2 to the x, and then we have to multiply by 1 over natural log of 2 out in front. And then we keep in mind when we're finding the antiderivative, it's not a unique answer. We can add or subtract any constant. So we do a little bit of simplifying. We have x cubed minus 2e to the x minus a negative, so plus 1/4 x to the negative 4. minus 3 natural log of the absolute value of x minus 1 over the natural log of 2 times 2 to the x plus c. Okay, so step 1 was find the general antiderivative. Step 2, we need to use f of 1 equals 5/4 to find c. Okay, so we have that f of x equals x cubed minus 2e to the x plus 1/4 x to the negative 4 minus 3 natural log of the absolute value of x minus 1 over the natural log of 2 times 2 to the x plus c. So if we plug in 1 for every occurrence of x, it will be equal to 5/4. So 5/4 is equal to 1 cubed minus 2e to the first plus 1/4 times 1 to the negative 4 minus 3 natural log of absolute value of 1 minus 1 over the natural log of 2 times 2 to the first power plus c. All right, so we have 5/4 is equal to 1 minus 2e. 1 to the negative 4 is just 1, so plus 1/4. Natural log of 1 is just 0. So minus 3 times 0 is just 0. And then minus 2 over the natural log of 2 plus c. So on the right-hand side, we have this 1 plus 1/4. That's 5/4. We could technically subtract 5/4 from both sides. Right, so the 1 and the 1/4 together give me 5/4. So if I subtract 5/4 from both sides, we would have 0 equals negative 2e minus 2 over the natural log of 2 plus c. Add 2e and add 2 over the natural log of 2 to both sides. And we would get c is equal to 2e plus 2 over the natural log of 2. And then step 3 would be to plug in c. We take our value for c and we plug it in to our antiderivative. So we'd have f of x is equal to x cubed minus 2e to the x plus 1/4 x to the negative 4 minus 3 natural log of absolute value of x minus 1 over the natural log of 2 times 2 to the x plus 2e plus 2 over the natural log of 2. So just basically that problem seemed a little intense because it was written to involve all antiderivative rules so that we can get it all into that one problem. But make certain you're comfortable with the idea that if you're wanting to find a specific antiderivative, you just find the general antiderivative and then solve for c is all we were using there. All right, so the next one, we are asked to evaluate the following integral. So we have 6 times x plus 1 times 7x minus 8, all divided by x cubed. Okay, so we notice that we're being asked to evaluate an indefinite integral. So my answer should be a family of functions. We know that we can either use our ideas from 4.1 or 4.2 to evaluate the indefinite integral. To use the ideas of 4.1, it has to either be written as a sum or a difference, or it needs to be able to be rewritten as a sum or a difference. If we can't use the ideas from 4.1, then we can use the ideas from 4.2, which is use substitution, but we would need to be in one of those three cases that we discussed earlier. If you remember earlier, I said that the one we were looking at earlier, we couldn't rewrite because we didn't have a single term in the denominator. Now we do have a single term in the denominator, and so we can rewrite this. You could try to play around with it and try to figure out a way to make use substitution work, but you're not going to be able to get it to work. And so I'm not going to take the time now to play around with that, but I'm just going to tell you that we will just need to algebraically manipulate this. So we're going to need to FOIL that expression in the numerator. So if we FOIL that out, we would have 7x squared minus 8x plus 7x minus 8. If we combine like terms, that would give us a negative x. And then we could distribute that 6. We'd have the integral of 42x squared minus 6x minus 48 all over x cubed dx. And then now we can break it up into three separate fractions, right? So 42x squared divided by x cubed minus 6x over x cubed minus 48 over x cubed. Right, so 42x squared over x cubed, the x squared in the numerator cancels out with all but one of the x's in the denominator. So that becomes 42 over x. So 42, I'm going to write that as 42 times 1 over x minus 6x over x cubed. The x in the numerator cancels out with one of the x's in the denominator. So that gives us 6 over x squared, which I'm going to write as 6x to the negative 2. And then minus 48 over x cubed, I'm going to write as 48x to the negative 3. So we see that we're dealing with a sum and difference of three basic functions, and so we can just find the antiderivative of each. So the antiderivative of 42 times 1 over x is going to be 42 times the natural log of the absolute value of x minus 6 times the antiderivative of x to the negative 2. We're going to use that backwards power function, or the backwards power rule. We're going to add 1, negative 2 plus 1 gives us negative 1. We're going to divide by that new power out in front. And then minus 48 times the antiderivative of x to the negative 3, we're going to use that backwards power rule. We're going to add 1. So negative 3 plus 1 gives us negative 2. And then we're going to divide by that new power out in front. So we have 1 divided by negative 2. And then we remember we're dealing with a family of functions, so we have that plus c. So I can do a little bit of simplifying here. I have 42 times the natural log of the absolute value of x plus 6x to the negative 1, because we have negative 6 divided by negative 1 gives me a plus 6. And then minus 48 divided by negative 2 is going to give me plus 24. X to the negative 2 plus c. So this would be my family of functions, my general antiderivative. Okay, so I'm not going to have time to do the entire number 12, but let me at least get you started and get you, and then I'll write up the solution for you by tomorrow morning and get that posted on the Math Learning Center's webpage. Okay, so the marginal profit function for a cell phone company is given by p prime of x equals this whole thing. So 2x to the 5/3 divided by the square root of x to the 8/3 plus 5/13 minus $4 per cell phone. where X is the number of cell phones sold. If the break-even quantity for this company is 64 cell phones, find the company's profit when 216 cell phones are sold. Okay, so we're basically given the derivative and then asked about the original function, the profit function. So we're wanting to go backwards. We're wanting to find the antiderivative. We're given information to find the specific antiderivative, right? We're given the break-even quantity. And so we first need to find the general antiderivative. So find the general antiderivative. Okay. So we need to find the antiderivative of p prime, and that's going to take us one step back. That's going to get us to the original profit function. So we're needing to integrate p prime of x. All right, so if I plug this in, we have 2x to the 5/3 over the square root of x to the 8, this little neater, over the square root of x to the 8/3 plus 5/13 minus 4 dx. Okay, so the first thing we have to realize is we are dealing with a difference in my integrand. We know the integral of the difference is the difference of the integral. So I can break this up into two integrals. And it needs to be broken up into two integrals here. So we have 2x to the 5/3 divided by the square root of x to the 8/3 plus 5/13 dx minus the integral of 4 dx. Okay, and the reason why we have to break it up into two integrals here is because this first integral is going to involve u substitution, and the second one isn't. Okay, and so if we tried to leave it as is, we would attempt to use u substitution and we would get stuck because the first one is going to involve u substitution and the second one is not. Okay, so let's deal with the two integrals separately. Let me use a different color. Let's say this is A and this is B. All right, so if we come down here for A, we have the integral, and I'm going to rewrite A. So that whole denominator is raised to the 1/2 power. So I'm going to bring that up in the numerator, raised to the negative 1/2 power. So x to the 8/3 plus 5/13 raised to the negative 1/2 times 2x to the 5/3 dx. Okay. And then I'm going to come over here and write b. We need to find the integral of 4 dx. What's the antiderivative of 4? 4x plus c. All right, so that one's easy. But this one over here, we're going to have to use u substitution. I'm going to tell you what we're going to do, but then I'm going to stop there because I unfortunately need to run. This right here is my u, because I'm dealing with a function raised to a power times some other stuff. And so we'd identify our u as x to the 8/3 plus 5/13. And then we would carry on just like we did earlier. Okay, so sorry I wasn't able to finish up that last problem, but I will get that written up for you and that will be posted by tomorrow morning. Good luck with your studying, and again, remember that there will not be a week in review the next 2 Tuesdays, because next week's the week after an exam, and then the next Tuesday is right there before Thanksgiving. But then the Tuesday after Thanksgiving, that will be our next and final week in review, and that will be to review for your final exam. So good luck with your exam 3. Have a nice Thanksgiving, and then I'll see y'all after Thanksgiving.